Number 9 asks us to sketch a few polar curves. And this first one, just based on its form, we know this is a circle that passes through x equal -4 and the origin. And I know it's x because it's cosine. And cosine polar curves tend to be situated along the x-axis. So it's going to pass through -4 and the origin. So it would be a circle, something like that. Has its center, obviously, halfway in between, which is at -2. But that's what I mean by label. The -4 is kind of important that you label. You don't really have to label the 2 since it's a circle. Okay, this next one, just based on its form, I know this is a cardioid. And because it's got a y, it's going to somehow be situated along the y-axis. But the best way to figure this out is to plug in some values and plot them, because I already know it's a cardioid. So I'm going to plug in these nice values, which are the quadrantal angles. The corresponding r, when theta is 0, r is going to be -1. When theta is pi over 2, sine is 1, so I'll get 0. When theta is pi, sine is 0, so I get -1 again. And when it's 3 pi over 2, sine is -1, so now I get -2. So if I plot those, go out -1 and then 0, that's going to leave you right there. Go out 0, doesn't matter what you do with the angle. If you go out 0, you're at the pole. Now go out -1 and then rotate through a positive angle of pi, which will put you on this other side. And then now finally go out -2 and then rotate 3 pi over 2, which will put you here. So we can see that this draws sort of our standard cardioid, but it was presented in a different way. So something like that. And it wouldn't hurt to label these main points that I found as I went through there. But I'll certainly be able to see how you plotted it if you show me the values that you calculate. All right, the last one here. Again, by the form, we know this is a rose curve. And since this is an odd number, there's going to be 5 petals on this curve. So if I take 360 and divide it by 5, I'm going to get 72 degrees between each stem, where the first stem is on the x-axis because this is cosine. So when I put in 0, for example, you're going to see cosine of 0 gives you 1. So the first one, let's use a different color here, is going to be out here at 1 at 0 degrees. And then the next one's going to have its stem at 72. Well, that'd be somewhere like maybe there. So 72 degrees, you'll have a stem. And then if you keep going, the next one's at 144. Well, 135 is right in the middle, so 144 is a little bit beyond that. So here's the stem at 144. Then the next one, if you add 72 to that, that's going to put you at 216. So this is 180, so around 30 degrees past that, a little bit more than 30 degrees, but anyway, something like this. So that's going to have its stem there. That's 216. And then if you go another one, it's going to put you at 288. 288 is 270s here, so 288 is a little bit past that. So you have one with the stem there. And if you go one more, it's going to get you back to 360, which is where that original one was. So mine looks a little off, but we'll just say I'm just going to draw now petals with those stems that I've designated. This one's a little far out. I'm going to put it there. I got a little excited and got that one even farther out. So something like this. So we know it's a 5. That's pretty bad. I got a really fat one there. But anyway, it's a 5-petaled rose curve where you do want to label these stems. And I believe I said this one was 272 with a 288. All right, now number 10 wants us to find the slope of the line tangent to this equation, this polar equation, when when theta is pi over 4. And so to find that slope, I know that means I want to take my derivative, and then I will plug in theta equal pi over 4. So let's take the derivative. But we know the derivative comes from finding the derivative with respect to theta of r, which is sine squared, times sine. So this is the derivative. What I'm doing here is this is the derivative of y, but y is r sine theta. And so it's the derivative of r times sine theta plus the derivative of sine theta times r. So here's my r again, sine squared. Derivative of sine theta is cosine theta. And then the denominator is the derivative of cosine, which is r cosine, of the x, which is r cosine. So that's going to be the derivative of r, which is sine squared, times cosine, plus the derivative of cosine, which is minus sine, and then times r. So here's my r, and then minus sine. So there's the derivative. Well, there's the setup of the derivative. Let me actually take it. Taking the derivative of sine squared, it's going to be 2 sine, and then the derivative of sine is cosine. So it's going to be 2 sine theta cosine theta times sine. And then this is just sine squared cosine theta. And in the bottom, I've got 2 sine cosine theta times cosine minus sine squared times sine. And as I said, I'm going to take all of this and evaluate it at pi over 4 to get my slope. So I'm going to do that now because I don't have to simplify any further if I do it now. And the nice thing about sine and cosine of pi over 4, you get 1 over square root of 2 from all of those. So everywhere I see a sine or a cosine, if I were to plug in theta equal pi over 4, theta equal pi over 4, I'm going to get 1 over square root of 2. So I'm going to get 2 times 1 over square root of 2, 1 over square root of 2, 1 over square root of 2, 3 of them, plus, again, 1 over square root of 2 squared, and one more is 1 over square root of 2 cubed yet again. And then here in the bottom, again, 1 over square root of 2 from 3 of them, so I get 2 times 1 over square root of 2 cubed minus 1 over square root of 2 cubed. So I think it's pretty clear I can factor 1 over square root of 2 out of the top and bottom, or you can combine them. It can probably be easiest to just say that. I got 3 of them up here in the top. Let's do it that way. Down here in the bottom, I got 2 minus 1. So I have just 1 over square root of 2 cubed in the bottom, just treating these like they're x's, 2x and 1x, 2x minus 1x. So canceling those out, I get a slope of 3.